Oh, hello again. Eager to learn, are we? Fantastic. Today, we are going to explore the wonderful world of thermodynamics. Thermodynamics is the branch of natural science concerned with heat and temperature and their relation to energy and work. There are three types of systems, and they are distinguished by what is allowed to cross through the boundaries. Be good, be good. So, the three types of boundaries are open, closed, and isolated. Now, in an open system, energy and mass are both allowed to cross through the boundaries. In a closed system, only energy is permitted to go through. And in an isolated system, well, no luck there, because nothing's getting through that little bugger.
What's up, guys? So, you should know that there are two types of properties when dealing with thermodynamics: intensive and extensive. Intensive properties are physical properties and do not depend on the size of the system or amount of material in the system. Some intensive properties include density, pressure, and temperature. Extensive properties are dependent on the size of the system or amount of material, and they include mass, energy, and volume. A thermodynamic state is fully defined when two intensive properties are known. If you know the extensive properties of a system, they can be changed into intensive properties by simply dividing by mass or the number of moles.
Oh, hello. As you probably know, thermodynamic calculation can get a little tricky. To simplify the calculation for you less intelligent people, we assume gas to behave as an ideal gas. We use the equation PV equals NIT, or the equation PV equals MIT, where P is the pressure, V is also the volume, M is the mass, R is the specific weight, and T is also temperature.
Hey, so yeah, work. One important thing that you need to pay attention to when dealing with work is the sign of convection. If W is greater than 0, work is done by the system on the surrounding. If W is less than 0, work is done by the surrounding on the system. To solve for work, we take the integral from state 1 to 2 of the pressure times the change in volume. Let's look at the 4 different cases when using the work equation. The first is called an isobaric process, where pressure is constant. First, we set up the original work integral, and then we pull out pressure because it is constant. After taking the integral, all you're left with is pressure times the volume 2 minus volume 1.
The second is the isochloric process, where volume is constant. This is perhaps the easiest to calculate. First set your original work equation. Since V is constant, the change in volume will go to 0 since there is no change. So no matter what your pressure equation is, since V1 equals V2, this integral will always equal 0.
The third is an isothermal process, where temperature is constant. Recall that PV equals mRT. Now, in a closed system, M is going to be constant. R, well, that's defined as a constant. And we've already been told that T is a constant. So, every single variable on the right side of your equation is constant. So, we can just give that variable C for constant. So, now you have C equals PV. You can rewrite this to solve for pressure as P equals your constant value over volume. Now, set up your original work integral and substitute C over V in for your pressure. You can pull out C since it's constant, and all you're left with is the integral from 1 to 2 of the change in volume over volume. When you solve this out with basic calculus, you're just going to have your constant times the natural log of volume from 1 to 2.
How do we determine work when PV to the N is constant and N is a constant? So, if N is not equal to 1, PV to the N equals C, and C is a constant. we can rewrite this as P equals CV to the negative N. You write out your original work equation, and then you plug this in for P. You factor out C and solve it using calculus, and your work is equal to this.
Heat, we use the letter Q. Q is greater than 0 if heat from the surrounding is added to the system. Q is less than 0 if heat from the system is rejected to the surroundings. If a system is closed, then the change in that system energy simply equals the change in energy transferred across the system's boundary due to heat and work.
Enthalpy is defined as thermodynamic potential. It is equal to the internal energy of your system plus pressure times volume. We can use enthalpy in a specific energy balance or a process where pressure is constant. Recall the work equation when pressure is constant. Work from state 1 to 2 simply equals your pressure times volume 2 minus volume 1. Substitute the work equation when pressure is constant into your heat equation, and you'll see that the change in enthalpy simply equals the heat that was added to your system.
But what about heat in constant volume? Great question. We can do the same analysis that my colleague Connor did previously. However, remember that when volume is constant, your work is 0. So your heat would simply equal to the change in the internal energy of your system.
So there you have it. You pretty much know thermodynamics now. Hopefully everything we've taught you today deters you from becoming an engineer. Because you know what? It's really hard. Peace.
Super süß, super sexy, super easy, super geil.